Good morning. We are getting very close to midterm 4. We've got a review, some review problems that we'll be looking at today. So once again, I have some examples of problems. I have the midterms from previous years. So here's an example of a midterm. We have a second one of these. We'll take a look at each of these problems and talk about them. And so let's go ahead and get started. Again, the format, 1, 2, 3, 4 problems, A, B, C, D, different parts in the problem when we take a look at these. All right, first problem, so coming from chapter 17 maybe, using the ideal gas law. We've got a storage tank, we've got a bunch of nitrogen inside at 270 kilopascals pressure, and temperature. Now that's got to get converted to absolute temperature. That's got to get converted into kelvins. And then they start asking questions about this sample of gas molecules. So let's take a look at that. So here's the container. I drew a little picture, still have those diagrams. We're in thermodynamics, but the diagrams are still really, really handy. And there's a bunch of nitrogen N2 molecules that are diatomic. It says that we're going to start off with 37,500 grams. I went ahead and just put it in grams of N2 molecules. There's the pressure, 270 kilopascals. And then the temperature, once we've adjusted to kelvins, should be 298 kelvins. So there's the temperature. Now, using the ideal gas formula, that will allow us to go in and estimate what volume this would be taking up. I need the number of moles. I have the temperature, I have the pressure, I know what the gas constant is, big R, but I need to know the number of moles. So we'll take the 37,500 gram total mass of the sample and divide that through by a molar mass. Now how did I get the molar mass? And nitrogen molecules exist as diatomic molecules, two nitrogen atoms stuck together, so a couple of nitrogen nuclei with their surrounding electrons. And each of those is 14 grams per mole, so that doubled would give us 28. Okay, so that's what I've got here is 28 grams per mole. That says that the sample contains 1,339 moles of nitrogen molecules. So for the volume, we can put in the number of moles of nitrogen molecules times big R, the constant, 8.314, joules per mole per Kelvin, times the absolute temperature. Don't forget to convert into kelvins. That's one of those things that I feel like is essential, and I take points off. I do. So if you've forgotten to convert, that is a big deal. It's not a small issue. It's important. And then standard units for the pressure. So I got standard units everywhere. Big R is in standard units. It's telling me that the volume I would need for this gas at this pressure and temperature and number of moles, I would need a volume of 12.3 cubic meters. So it's a good sized container. Cubic meters are pretty big. That's 12.3 cubic meters. Now in part B, it says we're going to add to this sample. So we're now going to take an additional 15.5 kilograms of nitrogen. That's going to bring the total. Oh, you know what? Did I calculate? I did calculate it right. Okay, good. I was thinking I did the numbers differently, but this seems fine. So initially we had 37.5 kilograms. We add 15.5. So that bumps this up to 38, and then 15 more is 53. I think we got it right. So this was the amount we started with, and then we added more. Now, we've looked at using ratios with the ideal gas law. This is a good example of saying, hey, the pressure is going to be, well, the pressure is going to go up, the temperature is going to stay the same, the volume is the same. So this is a tank. It's not changing its volume. So if volume is staying the same and temperature is staying the same, I can take the ideal gas law and use a ratio approach. I can say ratios of pressure to pressure, volume to volume, N to N, R to R, T to T, and then I can leave out whatever is unchanged. Now, the gas constant never changes, so I don't have to include that in a ratio. And then volumes are the same and temperatures are the same. So what I've got on the left side is the ratio of the new pressure compared with the original pressure is equal to the number of moles compared with the original number of moles. Now I could go in and calculate how many moles there are with the addition of nitrogen, but I could also continue that ratio and say that the ratio of the number of moles after and before is equal to the mass after and before. So the pressure is going to go up by that ratio. So it's the 270 kilopascals times the new amount of mass divided by the original amount of mass, and that will give me a ratio of molecules. That'll tell me how the pressure goes up. Okay, just using the ratio. And so it's going to go up from 270 kilopascals, it's going to go up to 382 kilopascals is what that works out to be. On part C, it starts asking about properties of some of the individual molecules. So it says, what would the VRMS be of the nitrogen molecules before and after adding the additional nitrogen? So the VRMS speeds only depend on temperature and the molar mass. The temperature didn't change, and the molar mass didn't change. We're going to have to talk about that in a little more detail. So that's a factor of 3, big R, same temperature before and after at 298 kelvins, and the molar mass stayed at 0.0280 kilograms per mole, and then we got the square root, and carrying out that calculation, checking all the units had better cancel out. Let's see, moles cancels moles, kelvins cancels kelvins, joules divided by kilograms leaves us with meters squared per second squared, and then taking a square root leaves us with meters per second. So 515 meters per second before and after. Now, one detail, well, it's not just a detail, it's an important feature. When we talked about molecular speeds, remember, the VRMS speed will be different if it's a different isotope. Different isotopes have different numbers of neutrons, so there are other isotopes of nitrogen, I want to say nitrogen, that's not true. I don't know if there's other isotopes of nitrogen that are stable. I need to go check that too, I guess. 14 is certainly stable. 14 is the dominant isotope for nitrogen. But if there are other isotopes of nitrogen around that are stable, I've really got to check that. Then the 0.028, in terms of the VRMS, it really only applies to those molecules made out of two nitrogen 14s. So we need to take 2 of the nitrogen 14 atoms, combine them to form a molecule, and that's what the VRMS refers to. All right, so it's not so much an issue for us, just something I want you guys to be aware of. Anyway, 515 meters per second sounds similar to what we've gotten before when we do temperatures around room temperature for molecules with molar masses like nitrogen or oxygen. And then finally, it asks in part D, what is the internal energy of the entire nitrogen sample before and after? So the internal energy is going to depend on the number of moles. If I have more nitrogen, that's on average going to give us more total energy. And then 5/2 RT. So nitrogen is diatomic. That means I have to include translational and rotational kinetic energies. And so the internal energy values will work out to be 5/2 nRT. In this case, the number of moles I did have to go in and calculate the number of moles. In the sample with the additional nitrogen, the number of moles went from 1,339 to 1,893 moles. So those are the internal energies before and after. Now, how big was this? This container is pretty big, right? And it's pretty high pressure. So we're going to have quite a bit of energy. So the energy worked out to be 8 million joules, 8.29 million joules, with the original sample of molecules. And then that went up to 11.7. Does that seem right? 6, 2, 2, yeah, okay. 13, yeah, probably. So it went up to 11.7 million joules once we have the additional nitrogen molecule. So the internal energies for these samples of molecules in the gas phase is going to, for the diatomics, it's 5 halves nRT. For the monatomics, it's 3 halves nRT. And that's going to tell me how much internal energy those molecules have. Questions on anything? All right, in problem 2, let's see. There's a molar mass for carbon, there's a molar mass for oxygen. No, we didn't use those. So I don't know why they're there. They just ended up there in a list of different molar masses. Problem 2. So now what we're going to do is we're going to take a look. This looks like that's like chapter 17. This looks like chapter 18, actually. And it's a chunk of ice. It's a big chunk of ice. 5 kilograms, you know, big chunk of ice, water ice, at negative 70 Celsius. So it's cold. This is not your normal freezer ice. This is at a really low temperature. So it's at minus 70, and it's being added into a 3 kilogram sample of water that's at 30 Celsius. Now, what's gonna happen? There is so much ice, I am thinking, and it's such a low temperature, I'm guessing that this amount of ice would be able to take this smaller sample of water at 30 and maybe bring it all the way to 0 and then begin to freeze part of it. So we're used to thinking, hey, if you put ice in water, the ice melts. But in this case, I'm thinking if you put ice in water, some of the water is going to get frozen because it's at such a low temperature. And we're treating this within a calorimeter. So we're treating it as if it's inside an insulated container. Now, it gives me a bunch of specific heats. For the ice form for water, I doubt we're going to get to use vapor. It's steam. I should really probably say water vapor. There's a heat of fusion, which we're going to need. That's freezing. Vaporization, I just don't think that's going to come up, but we'll see. So anyway, again, it's a more complete list, and I have to pick out the items that I want to be able to use from that list. So let me start with this. I'm going to start out with the water, the 3 kilogram sample at 30 Celsius, and I'm going to ask about 2 possible steps we could take. The first step would be to remove energy until the 30 Celsius water is at 0 Celsius. And then I'm thinking, let's keep removing water and freeze all of it. So I'm going to take the water, lower its temperature to 0, and then freeze it. Now, I labeled this process as Q1 and this one as Q2. Q1, that's a specific process. MC, delta T. There is the M. There is the specific heat. Now, I got to be careful with this too. So let's take a look. So with the water-specific heat, this is in joules per kilogram per Kelvin. Now, I could have left it that way. I didn't. I converted it into kilojoules for whatever reason. So now it's kilojoules. It became 4.186. So watch the units on these specific heats. There could be grams or kilograms on top. There could be joules or kilojoules. Joules or kilojoules on top, grams or kilograms in the denominator. And then the Kelvin here is no different from Celsius, since it's a delta T formula. So 3 kilograms times the specific heat, I think I got the units correct, it goes with those numbers, and then 30 kelvins is the amount we're going to drop it. We're going to have to pull out 377,000 joules of heat from the water to bring it down to 0, and then we're going to phase change it. We're going to freeze all the water. So here is the water. It's going to lower its temperature to 0, and then as we draw more thermal energy out, it's going to freeze. It's going to undergo a phase change. So that's 3 kilograms. A phase change requires 338 kilojoules per kilogram, and again, I changed those numbers into kilojoules, and it worked out to be 999 kilojoules. So that's how much heat we have taken out. What should we do with all that energy? And the first thing we want to do with this amount of energy is say, let's take the ice, which is at minus 70, and let's bring it up to 0. Now, what's that going to give us? It's going to give us both samples, the 3 kilogram sample and the 5 kilogram sample at the end of this third process are all going to be at 0 Celsius, and they're all going to be in the solid state. They're all going to be ice. So let's see what that does for us. So for this process, how much heat is that going to require? Well, it's another specific heat, so that's 5 kilograms times, now they tell us the specific heat for ice is 2.10, now I switched to kilojoules, per kilogram per Kelvin, times 70 Kelvin. That's a bigger, it's a smaller specific heat than liquid water, but it's a bigger temperature range, and this works out to be, and it's a bigger sample too. So it works out to be 735 kilojoules. Okay, so where are we right now? How much heat do we have to work with? I took out 377 kilojoules, and then I took out an additional 999, but then I put back 735. That means that I have, this is my bookkeeping, I have 641 kilojoules of thermal energy or heat that I have not assigned anywhere yet. So I have leftover heat. Now at this point, what we've determined is that putting this heat back in, that is not going to be enough to melt all the ice. We are going to have a mixture. So it turns out that once we hit equilibrium, we will have a water-ice mixture, and that tells us the temperature will be at 0. So what we have now is 5 kilograms plus 3 kilograms. We have 8 kilograms of ice at 0 Celsius, and we have this much heat, 641 kilojoules left that we can assign. So I'm going to come back and melt some of the ice. So I know we froze all the water to start with, but now what we can do is, since we've got the whole sample on the same page here, they're all frozen at 0 Celsius, now we can say the addition of 641 kilojoules, how much ice would that melt? And so I'm taking the specific formula. This time I'm solving it for M. So M is taking all of that heat, dividing it through by the specific heat, by the latent heat, 333 kilojoules per kilogram, and it says that we have enough energy left that we could melt, not quite 2 kilograms. So I got 8 kilograms of ice, and we melted 1.92 kilograms. That is going to leave us with 1.29 kilograms of water at 0 Celsius and 6.08 kilograms of ice. So we did freeze some of the water. Some of the water that started out liquid is now frozen into ice, and some of the water is remaining water. So that's kind of the bookkeeping we have to do on these problems. And the presence of both specific heat processes and the latent heat processes, both of those combined, means that we have to be a little careful. We have to kind of do some back and forth here. We can do a couple of processes, see what we're looking at in terms of energy, do one more process, see how much energy we have available. We got everything at the same temperature, same phase, and then we use the remaining energy to determine how much water, how much ice we would have. Okay, it could have been, you know, if the ice were at a really low temperature, maybe we freeze all the water, or maybe some of the more of the ice melts. Maybe we end up at a higher temperature or a lower temperature. So depending on numbers, the size of the samples, there's a range of possible final outcomes in terms of what the sample consists of. All right, questions on that? So yeah, definitely chapter, I want to say 18, but it actually was 19, huh? Chapter 19, I think, when we looked at specific heats. So in problem 3, we're looking at, there's a lot of stuff in 19. We are going to take a sample of nitrogen at, you know, room temperature and room pressure, and we're going to compress it adiabatically. So we're going to take a 5-liter sample and compress it to 1 liter. Now, you can't, let's see, oh, they say draw a PV diagram. So you got to draw a PV diagram whether they ask to or not, right? So here's pressure, here's the volume. Those are a couple of isotherms. So when I'm drawing an adiabatic process, I want to get those 2 isotherms in place, and if we're compressing the sample, that means that the molecules are all inside the container, and the compression is going to dump energy, it's going to transfer energy into those molecules. Temperature is going to go up if we compress adiabatically. So we're not allowing any heat to escape, and that means that the temperature will head off towards a higher and higher isotherm. So here's point A, here is point B. Now, the information that was given, they gave us starting temperature, starting pressure, and starting volume. And we're going to compress to some final volume, VB. Now, if you go back and you look at lecture notes, we introduced what we call the super adiabatic formula, and that's what I'm going to work from here. So in the super adiabatic formula, we showed that the ratios of temperatures are proportional to the ratios of pressures and the inverse ratio of volumes with some of these crazy powers. So we had powers of 1 over CV, 1 over CP, 1 over R. So go back, take a look at that super adiabat formula. So I'm just going to do parts of it here. If we take a TB over TA and set that equal to VA over VB, well, this power here is the R over CV power. Now, nitrogen is diatomic, so the specific heat at constant volume is 5/2 R, and the specific heat at constant pressure is 7/2 R. So, so we can use those when we are using the super adiabat formula, plugging those numbers in. Now, R over CV is going to be equal to, R over CV, it's going to be 2/5. So it's the inverse of that number, and that's what we've got here. Now, VA over VB, that's a volume ratio of 5. So there's this compression ratio of 5 going on, and that's how the adiabat formula works. I just need a ratio for one of the values. I need to know the ratio of either the volumes or the temperatures or the pressures, and then I can go through and solve for the other ratios. The ratio of temperatures then should be given by the inverse ratio of volumes to the R over CV, that's a factor of 5 to the 2/5, That is a factor of 1.90. So the temperature is going up by a factor of 1.90. We knew it had to go up. So if it wasn't going up, we would know something went wrong. We did the math wrong somewhere. But it did go up by 1.90. Plugging that into temperature A, multiplying that by 1.90, it says temperature went all the way up to 558 Kelvin. So that's a lot. The temperature went up by a lot when we compressed this by a factor of 5. So pretty significant effect. Then, in the second part of the problem, it asks about pressure. You know, here I got the temperature at point B. What about the pressure? Well, the super adiabat includes pressure ratios and says that the pressure ratio is equal to the inverse volume ratio. This time, the power is going to become Cp over Cv. And so that becomes a ratio of 7/5. So now it's 5 to the power of 7/5. That's more. That's bigger than 2/5. This is a factor of 9.52. So you can see when we compress adiabatically, we are transferring a lot of energy in. We're not allowing any of that energy to leave through heat. And as a result, temperatures went up a lot, pressures went up a real lot. 9.52. That's going to take us up all the way to 952 kilopascals. We're getting up to you know, close to 10 atmospheres of pressure. So, all right, so we got the temperature at point B, we got the pressure at point B, we used the super adiabat formula for that. For part D, D is asking what is Q, W, and delta E. So Q is the heat, and kind of by definition, when we derived the adiabat formulas, by definition an adiabat is a process where Q does not transfer. There is no heat transfer taking place. That's what makes it an adiabat. So it's an adiabat, Q is equal to 0, show your work. It's because it's an adiabat. Now, I feel like the next item we should look at is delta E. When I'm calculating adiabats, and I'm trying to calculate the work, I always think of the work as the area under the curve. But this curve is complicated. I don't want to integrate that. And so I'm going to go to something that's easy, I'm going to claim. I can always do delta internal energy as 5/2, it's diatomic, 5/2 nR delta T. That works for every process. So if I can find initial and final temperatures, I can find out how much the internal energy went up. Now that's 5/2. We need the number of moles. So we did a quick calculation, number of moles as PV over RT. I put in all the given numbers. So P at point A, V at point A, T at point A. I guess we could have done both. I mean, we should be able to show the ideal gas law gets the same result for numbers of moles before and after. I used the before numbers, but you could try the after numbers and see if they work. They should, okay? They should end up working. Let's see, the pressure went up by a factor of 9.52. The volume went down by a factor of 5, so that's 9.52 divided by 5. Yeah, I think that works because of these power. Yeah, it should work. So that's how many moles we have, 0.2053. Let's see, the volume's only 5 liters. It's not a very big volume, and it's only an atmospheric pressure. And so it's not that many moles. It's a fraction of a mole. Putting that into the formula, and the big item here, I guess, is the delta T. It says that the compression transferred 1,131 joules into those molecules. So 1,131 joules of energy in the molecules that was not there at point A. Now, for work, how are we going to calculate work? And once we have delta E, we can calculate the work. So I'm going to say that, as you guys probably know from class, from our lectures, that the sign on work doesn't necessarily make sense to me. And so instead, what I think of is there's the container with the molecules inside. I'm not letting any energy transfer through heat, and yet the internal energy is going up due to the work. Oh, the work coming in is equal to the increase in internal energy. Now, I did an absolute value. Officially, that's supposed to be a negative value of work when the work comes in, but I just called it 1131 joules going in, being transferred in. This is called work done on the gas, and officially it has a minus sign, but I prefer the diagrams. So there it is, 1131 joules coming in due to the compression, and that shows up as internal energy because none of it is leaving as heat. All right, so any questions on that? All right, let's move on. I guess we're down to problem 4, and then we'll take a break and we'll come back and look at an additional set of problems that we have set up. So problem 4 here says that we have a freezer. It's a 350 watt freezer. Now that refers to the rate at which energy is coming in to operate the compressor. So we're treating this freezer very ideally. I don't know if we should, but we are doing that. So let's see what happens here. So it's in a room at 25 Celsius, and the inside of the freezer is at minus 10. So that's keeping things frozen inside. And it says that what we want to do is make some ice cubes, and we want to take some water at room temperature at 25 Celsius and cool it down, freeze it, and then lower the temperature to a minus 10 Celsius. So that's, it sounds like 3 processes. So, and we'll get back to those 3 processes. I guess the first thing I outlined was the freezer itself. So here's the freezer. Here is a high temperature region out in the room. Here is the low temperature region inside the freezer. Here is the QL being transferred out. Here is the work going in to operate the compressor on the freezer. And then here is the QH leaving and going out into the room. Now this is a freezer. So the coefficient of performance is defined as how much heat are we bringing out from inside the freezer. We want to focus on Q sub L. So how much heat is being taken out of that low temperature region, and then divide that through by the amount of work we have to invest in order to make that happen. So now that's the actual coefficient of performance. I can rewrite the actual coefficient of performance as QL on top. The work can be written as QH minus QL. So I can write it all in terms of Q's, and the reason I want to do that is because once I get a formula with just Q's, I can take out the Q's and put in the temperatures, and that will give me the ideal formula. What we showed with the second law of thermodynamics, with, and this is definitely chapter 20 stuff we're looking at here, well, with the second law of thermodynamics, the Q over T, QL over TL equals QH over TH under ideal conditions. Now we're not going to get to those ideal numbers, but it says at least ideally the COP could be as high as TL over TH minus TL. So these formulas look the same, except I took the Q's out and replaced them with temperatures. Now these have got to be absolute temperatures, and again, I'm not very sympathetic if you come up and say, well, I use Celsius instead of Kelvin. How important could that have been? It was really important. So make sure that you're getting the temperature conversions that you need. Now the TL, the temperature within the freezer, Okay, I did this one wrong, huh? Let's see, this is 263. That needs to be 263, not 298. That's going to lower, it's going to lower the COP by 1, is what it's going to do. So this should actually be 7.51, not 8.51. This needs to be 263. It's not a heat pump, it's a freezer. And so I need to use TL, not TH. And yeah, it's going to lower it by 1. So, all right, let's see how that's going to affect everything. The heat being taken out, the QL, right from there, is going to be the COP times the work. Now this is supposed to be then 7.51 times 350, and that's going to lower the QL by 350. So this is going to become 2450? 2430. So 2430 watts is the rate at which it's coming out. I'm going to need to get that updated and corrected. All right. All right. I hope at least I'm catching these as we go through them. Again, I go through these, I feel like pretty carefully, but it's just not the same thing as presenting it and then starting to see these discrepancies that show up. Anyway, once again, if you guys find any errors in any of the work that I'm presenting here, let me know and I can get that information out to the whole class. All right, now what we want to do is ask specifically if I'm going to use this freezer to make some ice, 1 kilogram of ice, I need to take it through these 3 steps. I need to take the ice from room temperature down to 0. That is a specific process. And then I need to freeze the ice, which is a latent process, ML. And then I need to lower the temperature a little bit more because we want the ice all the way down to -10. We don't want to put the ice in the water and have it start to melt already. We want it to be lower temperature. Anyway, so here it is, MC delta T, that first step, is going to require 104,650 joules. Step number 2 is M times L. That's going to be 300, that's the biggest step, 333,000 joules. And then finally that last step, lowering the temperature to -10, that's the specific heat for ice, and a delta T of 10. And so that's 21,000 joules. So if I add all that together, the freezer, in order to freeze this ice that I just put into the freezer, everything else in the freezer is already at -10. And now I'm taking some ice trays with some room temperature water, putting it into the freezer, and now what the freezer is going to do is it's going to take all of this heat and start moving it out of the freezer using the coolant, using the refrigerant. How much time will that take? Well, it's 458,650 joules that has to be taken out. And the QL, the rate, now notice this isn't strictly speaking an energy, it's actually an energy rate. It's a power. At what rate is the energy being taken out? And we miscalculated this. This is supposed to be, what did we decide? 26, not 24. 2630. So this is 2630 joules per second. And if I put that in, I'm going to get an answer. Now, this answer is not quite correct, but we got 154 seconds, which is like 2.5 minutes. It's going to take a little longer, but not too much longer. Okay. Now, this is assuming that the freezer is operating at the best optimal coefficient of performance possible given the temperatures, and that's really unlikely. So the coefficient of performances are probably more like 3 or 4 instead of 7 or 8. So it's probably going to take twice as long as this. Now still, what that seemed to be suggesting is that the ice should be frozen in 5 or 6 minutes. And we talked about that in lecture 2, that the old style freezers, those were serious freezers where you had a metal box and you had metal ice cube trays, and that's what I remember as a kid growing up, is you open up the refrigerator, open up the freezer part, and everything inside was, the shells were metal and the coolant ran right through it, and they were a little dangerous because if you reached in and touched the shells, you would freeze, you know, your finger would freeze to that, you'd pull it away, so you had to be a little careful touching the insides, but things froze really fast because of the good thermal conductivity of the metal shells and the metal ice cube trays. So, you know, that was a sensible thing to do, right? Let's get the ice frozen as soon as possible, and let's have very, very good thermal energy conductivity helping that process. Okay, so I will get back and get the numbers here corrected for that last problem. All right, I think that's a good place to take a break. We got through the first practice exam. Let's take a break, and then we'll come back and we'll do one more.